So welcome to Module 3 of the course. This week we will be covering concepts of confidence intervals and hypothesis testing. I have with me Professor Juan Hernandez, and we will start off with discussing the confidence intervals first. So what is a confidence interval? So a confidence interval is essentially a part of estimating a population parameter. So imagine that there is a population that we're studying, and let's say that we are trying to estimate mean of that population. So one way to calculate that mean would be to study each unit in the population and then get the data for that unit and simply be able to calculate the mean, which would be the population mean. However, in the real world, it's often the case that the population is very large and it is not feasible to study each unit in the population. So for example, imagine if we had to calculate the average income in the United States. So clearly, this would be a tall task because given the population of United States, one would have to reach out to each individual in the population and get the data for them. Clearly, this would require a lot of resources. So what would be the other way? Well, we can take a random sample from this population and calculate the sample mean, which would then be which could be used as an estimate for the population mean. However, even a better method than that would be to create an interval within which we can say that we are somewhat sure that the unknown population mean is contained.
Absolutely. And in that particular case, we then would like to be confident or to determine the level of confidence associated with that particular interval that we have calculated.
Correct. So we will take some time here and discuss what is accuracy and what is precision. And in Zybook, this participation activity 5.1.1 does an excellent job of describing what the two are. As an example, let's consider this target where we're trying to imagine that you're trying to hit this target right here. In the first case scenario, you see these red dots are all sort of scattered all around. Only one happens to be within the target. The others are outside of it. So Professor Juan, what would you say about precision and accuracy in this case here?
Well, certainly it is not precise, and let's come up with a definition for what do we mean by precise. Precision refers to the stability that the measurement has when it's repeated many times. So imagine that you were throwing darts at the target. You see that your darts are all over the shape of the target as opposed to being close to the center. So the hits not being close together means that you're not precise. However, when you throw the darts and the darts are grouped together, then you're being precise.
Exactly. So imagine this second case here. You'll notice that all of these darts are very much close to each other. They're very precise. But are they accurate? No, because the target is here and they're all off of target. So they're not accurate. They're very precise. Consider the case here. You can see that in this case, the dots are fairly within the target, so they seem to be accurate. But their precision is still not that great because they are not close to each other. And that leads us to this last target here, in which the red dots are right next to each other. The accuracy is good, and so is the precision. Whenever I think of confidence intervals, I always think that they represent a range of believable values for an unknown population mean. And what do I mean by that? So range of believable values mean, what is that range within which I can say that my true unknown population mean lies? If you notice this black line here with this dot here represents a population parameter. So it could be the population mean that happens to be 4, a value of 4. All these other dots are essentially different samples that are taken, and the sample mean is calculated. So you'll see that the sample mean tends to vary as we take random samples. And these are 20 samples. So clearly when you randomize a sample selection, each time you'll get some variability in your data, which is why your sample mean will be slightly different each time. What's more important though is this red line that represents the range of believable values that I just discussed. For example, in the first case, you can see that the lower bound tends to be around 1 and the upper bound tends to be around 6. The unknown population mean would be contained within this interval. So imagine if this value of 4 was unknown, it would be contained in this interval. In the second case, you notice that again, the interval contains the mean. In the third case, again, the interval contains the mean, and so on. And you'll see that there are 20 different intervals, out of which 19 contains the mean. Only one, this blue interval here, does not contain the mean. What this means is 19 out of 20 times this interval here is containing the mean. So 95%. That's 19 out of 20 is 95%. So let's move on to how do we define a confidence interval? So I think that Zybook does a great job of explaining that right here. And let's actually start with this equation right here. It says estimate plus or minus m. M represents margin of error. So what we're saying really here is that when you have an unknown population mean that you're trying to estimate, you can take out a sample, calculate the sample mean, and then that becomes an estimate of the population mean. But better than that, what we can do is we can put a margin of error around that sample mean. So we can say that you now have this lower bound and an upper bound, and then we can say that, okay, we are somewhat sure that the unknown population mean is going to be contained in that interval. That is what this margin of error represents. All it does is it takes you from a sample mean to a range of values. So estimate minus m, estimate minus the margin of error is your lower bound, and estimate plus the margin of error is your upper bound. We define the margin of error as the standard error times the critical value, which is calculated for a given confidence level. And the critical value is based on what we studied last week, which was the normal or the t distribution. And we will go into the formulas in a little bit, but essentially that's what this is. So we will start with the confidence intervals for population means. This is the case when we are trying to estimate the unknown population mean. The mean is the parameter in this case, and we will use the normal distribution, concepts from the normal distribution, to be able to create these confidence intervals. So let's look at this this one example here. So suppose that the mean final grade is estimated for all statistics classes taught at a college. The population standard deviation is 4. We are already given the population standard deviation. It's known from perhaps from the previous studies that have been done. The final grade for a randomly selected stats class with 9 people are, so what we have here is data for 9 students and their final grades in a stats class, and these are the grades. And the question is, we need to find the 95% confidence interval for the mean final grade. And when we say 95% confidence interval for the mean final grade, what we mean is the unknown mean final grade for that statistics class. So essentially what's happening is we're trying to calculate the population mean in this case, and we're using this one sample that we have collected from 9 individuals to be able to do that. Now, in reality, you would hope that the sample size is large enough. This is not a very large sample, but we get the idea. So the first step is to calculate the sample mean. So this is the sample mean. It's just you sum all the grades and divide it by 9, and that's your sample mean. Just a while back, we looked at the margin of error formula, and it was critical value times the standard error. The critical value in this case is this z star, and that's given as 1.96. You'll see that this there's a table in Zybook 5.2.1 that provides the critical values for some common confidence levels. 90%, 95%, 99%. The values are given here. So we use this value 1.96 as the critical score. Standard error is when you're calculating the confidence interval for a mean, the standard error is given as sigma, which represents the population standard deviation, which is given in this case as 4, divided by square root of n, in which case n is the sample size. So it's 4 over square root of 9, and that's how you calculate your margin of error. And then just by the definition of a confidence interval, we know that the interval is the sample mean plus or minus the margin of error. And the sample mean in this case was 83.222, and then the minus 2.613 is the lower bound, and then plus 2.163 is the upper bound. So you get this as your confidence interval. Now, once you have calculated the interval, it's very important to be able to provide correct interpretation of that interval. And so what we can say here is that we are 95% confident that this interval here contains the true unknown population mean final grade in this statistics class. It is often the case that we are not given the population standard deviation. In the example we just covered, population standard deviation was provided to us. But in a lot of cases, that will not happen. And so what do? What we can do is, instead of using the population standard deviation, we can use the sample that we have collected. We can calculate the sample standard deviation and use that instead. So now we're not just using the sample mean in the confidence interval, but we're also using the sample standard deviation that we have estimated. However, when we do that, we will not be using the z distribution. We will be using the student's t distribution that we studied last time. And just like the z distribution, where we had the critical values for the critical z scores, or the critical values for different confidence levels, we have the same case for the t distribution. It involves knowing what we call the degrees of freedom. We don't need to go into the details of what degrees of freedom are, but the only one important thing to remember is that the degrees of freedom always equals n minus 1 in our case here. So the sample size minus 1. So if the sample size is 30, the degrees of freedom are going to be 29. And this table here provides some commonly used degrees of freedoms, and alpha. Alpha is essentially just 1 minus the confidence level. If the confidence level is 90%, then alpha is 1 minus 90%, or 0.9, which will be 0.1. For alpha 0.05, we will have a 95% confidence level. So essentially, once you have this information, you'll be able to do any problems. So the margin of error calculation is the same. It's the critical t score times s. S is the sample standard deviation over square root of n. So once you have your sample, calculate the mean, calculate the sample standard deviation, and you will know your sample size. And then once you know your sample size, you know the degrees of freedom. Once you know your degrees of freedom, you know the confidence level that you're using that will be provided to you in the question. And once you know that, you'll know your critical t-score. And then once you know all of that, you know your margin of error. And then essentially the interval is the same. It's the sample mean plus or minus that margin of error. So let's look at this data that is stored in examscores.csv file that resides in the Zybooks cloud. This is also an example that is covered in Zybooks. So what I've done here is I have just printed the contents of that CSV file, and here are the contents. So you'll see that it has 50 observations for each of the 4 exams in a class, exam 1, 2, 3, and 4. And the task here is to calculate a confidence interval for exam 1 based on this sample data of 50 students. So if we recall, we had discussed the formula for confidence interval for a mean. And based on the z distribution, it was the estimated sample mean plus or minus a margin of error. And if we recall, the margin of error was the critical score, the critical z-score times the standard error. In Python, we can calculate that. And by the way, we also remember that we would use the normal distribution or the critical z-score when the population standard deviation is provided to us. And in this case, we're going to assume that it is provided to us and that it is 2.5. So in Python, we have 3 modules that we're going to be working with here. Pandas, of course, to be able to import the CSV file data. The math module, which we will use when we are calculating the standard error. And this is the critical one. We're going to use scipy.stats. That's the submodule stats. That includes a method to calculate the confidence interval, which is this, st.norm.interval. So the input to this method, st.norm.interval, the first is the confidence level. So we are going to be using a 99% confidence level, so that's why we have the 0.99 here. The second input is the mean of the sample mean that we have estimated using the sample. And the third input is the standard error. We're going to assume that the sigma, the population standard deviation, is given as 2.5. This line here calculates the mean. So our mean is calculated here. And this line here calculates the standard error. It's equal to the population standard deviation divided by square root of n, where n is the sample size. And we can calculate the sample size using this function here, the length function. This calculates how many rows of data we have. And we're only looking at exam 1. So how many rows are there? There are 50 rows. So essentially what this would do is calculate the value 50. And then we take the square root of it, which is in the formula of the standard error. And then the sigma is given right here, 2.5. So we use that, and that's how we get our standard error. And this is how we're going to calculate the confidence interval. So I'm going to just not print the values now, and I will print the confidence interval itself. So let's run this. You see that we get a lower and an upper bound. The lower bound 81.789, the upper bound is 83.611. So now that we calculated the interval, the next step that's very important is to be able to do its interpretation. One way to interpret this is to say that we are 99% confident that this interval right here contains the true unknown mean score of exam 1. Now let's play with this a little bit here. Let's say that I was to dramatically increase the sigma. So let's say I increase the population standard deviation to 12.5. So what would happen to the interval? We know that the population standard deviation is now large. If the population standard deviation is large, we know that our standard error is going to be large because sigma is in the numerator in this calculation. If the standard error increases, we know that the margin of error will increase. If the margin of error increases, we know that when we subtract and add margin of error to the sample mean, we should get a larger confidence interval, meaning that the lower and an upper bound will now be further apart. So let's make sure that happens. So all I've done is I've increased the sigma here, and let's run this again. And you can see that we get a wider confidence interval in this case because the population standard deviation went up. Now let's try to reduce it. Let's take it to 0.5. So remember it was 2.5 before, so I'm going to just go back to our original confidence interval. Now let's reduce it to 0.5, which means the standard error will go down. If standard error is now lower, that means our margin of error will be lower, and so we should get a narrower interval. So let's make sure that happens. And it certainly does. You can see that now the interval is much narrower. Now, we know that this sample size value here, I'm going to go back to 2.5. We know that this length of this data, which was returning the number of rows as 50, is going to be 50 before. What if we reduce this to, let's say, 10? So now the sample size has reduced to 10. We can see that the denominator now is smaller, hence the standard error will be larger. If the standard error is larger, the margin of error will be larger. And if the margin of error is now larger, we now should get a wider interval. So for the same value of sigma, if the sample size is reduced, our confidence interval should be wider. Let's make sure. Yep, you can see now it's a wider interval because of a smaller sample size. What if we increase the sample size to 100? Or even let's say 1000? Well, now the opposite will happen. The interval should get narrower. And that's exactly what happens. So this time we're using the same data, same exam, and now we're going to assume that we don't know the population standard deviation. So we're going to use the sample to estimate population standard deviation. So we will use the sample standard deviation to do that. And this time, because we're using the sample standard deviation in our formula, so we're going to use the t distribution as opposed to the normal distribution that we used before. So I'll just walk you through the steps. So this is where we import the data. This is another way to calculate the sample size. Remember, previously we calculated using the length function from the math module. Well, this is another way to do it. We can just count how many rows are there. Recall that when we use the t distribution to calculate the confidence interval, we require the degrees of freedom. And that's what this does. The df equals n minus 1. Degrees of freedom equals sample size minus 1. The mean, now we calculate the sample mean, just as before. And then we calculate the sample standard deviation using this STD method of the pandas data frame. This is the sample standard deviation. This is not the population standard deviation. Once we have the standard deviation, we can calculate the standard error, which is the standard deviation divided by the square root of n. So this is another way to calculate the square root. So we get our standard error, and then we can print out the confidence interval using t.interval method in scipy.stats. The inputs are, the first is the confidence level. This time we're calculating the 95% confidence level. The second input is the degrees of freedom that we calculated here. So we're referencing the same variable name. The third input is the mean, and the last input is the standard error. And so once we print this, we get our confidence interval. So again, the lower bound is 80 and the upper bound is 85. And the same rules apply here. If we increase the sample size, we make the confidence interval narrower. If the sample standard deviation increases, then because the standard error increases and the margin of error increases, hence the confidence interval gets wider. So just like we have confidence intervals for the population mean, we also have confidence intervals for population proportions. And in the case of proportions, the nice thing is that we don't have student t distribution to calculate the interval. We always use the normal distribution to calculate these intervals. Calculations for the margin of error is given right here in example 5.3.1, and it is z star, which is again the critical z-score, times square root of p hat 1 minus p hat divided by n. P hat here is the proportion, which we will study in a little bit, and it's times 1 minus that proportion and then divided by n, which is the sample size. So let's just quickly read this example and then we'll know what p hat is. So in a survey of 1,200 randomly selected registered voters in a particular city, 348 people are in favor of banning public smoking. State and interpret the 95% confidence interval for the population proportions of voters in favor of banning public smoking. We say that 348 people are in favor of banning public smoking out of 1,200. The sample proportion here, which is what p hat represents, is 348 divided by 1,200. That's what's given here. And the idea here is to estimate the unknown population proportion. So once we have our p hat, in this case is 0.29, we can plug that into this formula. N is 1,200, and because we're calculating the 95% interval, therefore z is 1.96. Z star, I'm sorry, is 1.96. And so we get this margin of error as 0.026. And now we can calculate the interval. The interval is, again, it's just p hat plus or minus m, margin of error. P hat is 0.29, so we subtract 0.026 to get the lower bound, and we add 0.026 to get the upper bound, and that is our confidence interval. And then just like we discussed that it is very important to interpret the interval, the same is the case here. And in this case, the interpretation is fairly straightforward. We just say that we are 95% confident that the true proportion of voters who are in favor of banning public smoking is between 0.264 and 0.316, or 26.4% and 31.6%. So in Python, we can do the same example. The nice thing here is that we will use the same method from scipy.stats. We'll use the norm.interval method. The inputs will be the same as before, except that this time we're not using the means, we're using proportions. So the first input again is the confidence level. The second is not the mean, but p hat, which is the sample proportion. and the second is the standard error just like before, but this time is the standard error for the proportion. So our n, which is the total sample size, is 1200. That was the sample size in the example that we just did. Sample proportion was 348 divided by 1200. We use the formula for the standard error, p hat times 1 minus p hat divided by n, and then square root of the whole thing. And once we have that, we can calculate our confidence interval. Now, notice that in all these examples that we have done, we have not calculated the margin of error. That's because the method itself does that for you. So is there anything else, Professor Wan, that we need to discuss here?
Well, the only thing I would like to mention as a review for all methods is to, in the real world, to realize that since sampling is expensive, in other words, we keep saying that in the long term, we will be able to meet the requirements of the 95 or 90 or 99 level of confidence. We only take one sample. Most companies only use one sample. And that becomes very important because you have to establish that the sampling size is adequate to be able to have the correct level of confidence.
The first part of Module 3 discussion is about confidence intervals. Let's just read through some of the instructions here. So the instruction here says that we have a manufacturing process at a factory that produces ball bearings that are sold to automotive manufacturers. The factory wants to estimate the average diameter of a ball bearing that is in demand to ensure that it is manufactured within specifications. So suppose that we have a sample of 50 ball bearings. What we need to do is to construct a 90% and a 99% confidence interval for average diameter of ball bearings, of all ball bearings, okay? Not just this sample, but all ball bearings produced from the manufacturing process. So what is the idea of the confidence interval in this case? We're using the confidence interval to make sure that we are falling within some tight specifications of diameter of these ball bearings. The sample size of 50 is generated using Python's NumPy module, and this data set will be unique to you, and therefore your answers will be unique as well. So again, as it was the case in previous weeks, your data is going to be unique to you, and therefore your answers will also be unique. So if you see different answers from different students, this is the explanation for that. Running step 1 in the Python script generates the data, and then running step 2 calculates the confidence intervals, and then you have to answer these two questions about the confidence interval. The first question is simply about reporting the intervals. What is the 90% and what is the 99% confidence interval? And then the second question is about interpreting those intervals. So providing appropriate interpretation of those intervals, just like we have done with the examples that we covered in this video. And here's step 1, which is on generating your sample data. So we will run step 1, and you will see that it will generate the data and then it will print it for you. So here are the values that were printed. Each time I run it, I'll get a different set of values, again because we're randomly generating these values. So once you have generated the values, I would recommend that you don't run this step again. These are the values you're going to be using. So there are 50 diameters, and now we will construct the confidence intervals. Let's just run through this. Here we calculate the sample mean. We are given the standard deviation, and so we know that we will be using the normal distribution to calculate these intervals. We calculate our standard error, which recall is the standard deviation divided by square root of the sample size. And we're using the length function again to calculate the sample size. So that's our standard error. And then once we have our mean, the standard error, and the confidence level, we can easily use the st.norm.interval. St is, again, is the scipy.stats submodule. It's an alias for it. So we're going to be using st.norm.interval method to calculate the 90% confidence interval, in which case the first input is 90.90, 90%. Second input is the mean. Third input is the standard error. We print that. So here we're printing both the unrounded and the rounded. So we're rounding the values, and we're also printing the unrounded values. And similarly, we calculate the 99%. So let's run this step. So here's the output. You can see we have the 90% interval is given here. Here it's rounded. And then the 99% is given here. And here's the rounded 99%. So we have the two intervals. Now, we covered the case where we changed the sample size and we noticed what happened to the width of the interval. We reduced and increased the standard deviation, and we noticed the effect on the width of the interval. We never discussed what happens if we used a confidence level of, say, 90%, and then if we, let's say, increase it to 99%. So what happens to the interval? Obviously assuming that the mean and the standard error are the same. Well, let's see. 90% is 2.41 and 2.64. 99% is 2.34 and 2.71. You'll notice when the confidence level increases, the interval, the width of the interval increases as well. So why is that? Well, because we're trying to be more confident, and therefore in order for 99% confidence interval to contain the unknown population mean, we would have to increase that interval. Okay, so the lower bound will be lower than the first case, and the upper bound will be larger than the first case. So when the confidence level increases, the width of the interval increases because we're trying to be more confident that the interval includes the unknown parameter. When the confidence level decreases, because we have to be less confident about the interval containing the unknown parameter, and therefore the interval is narrower. So that's the explanation for that, and that is the explanation that you will include in your initial post. The second topic we will be covering this week is called hypothesis testing. So Professor Wan, what is hypothesis testing? What is the role of a hypothesis testing in estimating population parameters?
Okay, let's take a look first of all at what a hypothesis is. It's nothing more than an assumption about a population parameter. So hypothesis testing is a use of statistics to determine the probability that a given hypothesis is true. Let's look at an example. If I give patients counseling in addition to medication, then their overall depression scale will decrease. Another example would be if I give exams at noon instead of 7 p.m., then the students' scores will improve.
So I'm guessing that what will happen here is we will make some kind of a claim, and then we will collect data, and then we will try to sort of evaluate the statistical significance of that data, whether or not it supports the claim that we made or not.
That is correct.
Okay. And I suppose for hypothesis testing, we probably, when we talk about making claims, we probably have some kind of a proper way of establishing one claim. And then if that claim is, say, rejected, then maybe there's an alternative claim that we can fall back on. Is that correct?
Yes. With a null hypothesis, what you're doing is either you reject the null hypothesis or you fail to reject the null hypothesis. And the alternative hypothesis, symbolized by H sub A, this is a statement that you will adopt if there is a strong evidence, sample data, against the null hypothesis.
Okay, so just like Professor Wan said, each hypothesis test starts with identifying the appropriate null hypothesis and the alternative hypothesis. The null hypothesis will always be a statement that will include the equal sign, so perhaps the mean equals a certain value, or perhaps the proportion equals a certain proportion, a proportion value. And the alternative hypothesis, on the other hand, is what we will be focusing on if the null hypothesis is rejected based on the calculations that we will do. And in the alternative hypothesis, we will either have a less than the value that is covered under the null hypothesis, greater than that value, or not equal to that value. Example 5.4.1 does a good job of this, of sort of practicing with the alternative hypotheses. It says identify the type of each alternative hypothesis and state the corresponding null hypothesis. So let's say that the alternative hypothesis is that the average time spent sitting at a particular company's office is not 5.7 hours. So clearly is not means not equal to 5.7 hours. So this is the alternative hypothesis. The alternative hypothesis is that the average time is not equal to 5.7 hours. So what would be the null hypothesis for this? So we know that the null hypothesis should always include the equal sign. It will never be anything other than the equal to a certain value. And in this case, the null hypothesis will be that the average time spent sitting at a particular company is equal to 5.7 hours. The second example, patients given a drug recover from a disease in less time than patients not given the drug. So in this case, we have the less than case. And so we say that the alternative hypothesis is that the patients that are given the drug recover from a disease in time less than the patients that are not given the drug. And the null hypothesis for this would be that the patients given a drug recover from a disease in time equal to the patients that are not given the drug. We use the sample data to calculate what we call the test statistic. The test statistic is simply just either a z-score or a t-score, where we evaluate how far off that t or z-score is from the parameter that is being tested. So if we have the null hypothesis that the mean equals 20, we will calculate the test statistic for a sample that we have collected, and perhaps the sample mean, let's say, comes out to be 35. And the question then really is, under the null hypothesis, where the population mean equals 20, if we were to get a sample mean of 35, is that likely or is that very unlikely? And if it is likely that we can get a value of 35, then what we will not reject the null hypothesis. If the sample mean of 35 is not likely for a population that has a mean of 20, then we will reject the null hypothesis. The test statistic essentially then is a statistic that we can use to identify whether or not the estimate that we calculated is likely or unlikely, assuming that the null hypothesis holds. And so, Professor Wan, what is then the p-value now that we have the test statistic? What is the p-value and its statistical significance?
The p-value or probability value is a way of establishing whether we're going to accept, or I should say fail to reject the null hypothesis, or we're going to reject it. And if the p-value is less than the alpha value, the value that we're trying to compare against for validity, for example, 0.05 as an alpha value, if it is less than that amount, then we will reject. We will say that there is significant evidence to reject the null hypothesis. However, if the p-value is greater than the alpha value, greater than 0.05, then we will retain the null hypothesis.
Okay, so I think this is best covered with an example. So let's move on to an example of hypothesis testing, where we will be carrying out a hypothesis test for a population mean for which the population standard deviation is known. And so therefore, again, just like the confidence intervals, because the population standard deviation is known, we will rely on the normal distribution as opposed to student's t-distribution. So here's an example, 5.5.1 from Zybooks. So a popular electronics website wants to determine whether a smartphone has a 7.8 hour battery life, as claimed by the manufacturer in response to user complaints of poor battery life. So the website samples 10 smartphones and they calculate the mean battery life for using that sample, and it comes out to be 7.6. So clearly the claim is 7.8 hours, and when the website sampled 10 smartphones, they found the mean battery life to be 7.6. The population standard deviation of the battery life is given. So the population standard deviation is known. It is 0.57 hours. Does sufficient evidence exist that the battery life of the smartphone is actually lower than manufacturer's claim? Use a significance level of alpha 0.05. So there's a lot of information in this question, but we will take we will solve this problem in various steps, and the first step is to clearly identify the null and the alternative hypothesis. So, Professor Wan, what would be the null and the alternative hypothesis given this?
Okay, so let's relate the vocabulary to the symbols. The symbol for the null hypothesis is H sub 0. The symbol for the mean is the Greek letter mu, and as the problem states, the mean in this case is 7.8.
Yeah, just to clarify here, that's the population mean. So we're trying to say that the population mean equals 7.8.
That is correct. That is a population mean, and the mean for the sample is 7.6.
That is correct. So just like you said, the null hypothesis here in statistical terms says mu equals 7.8, and in words what that means is that the population mean battery life of the smartphone is 7.8. That is what the manufacturer claims. The alternative hypothesis is mu is less than 7.8. So we're saying that the manufacturer's claim may not be correct. We think that the population mean is less than 7.8. Why are we choosing less than in this case? Why are we not choosing greater than or not equal to? Well, because when we took the sample of 10 smartphones and we calculated the mean battery life, it came out to be 7.6. That's less than the original claim by the manufacturer. So we are inclined to test the less than case here as opposed to greater than or not equal to. So imagine if we were to get a value of 8.5 as the sample mean, which would be more than the population mean of 7.8, then I would be inclined to use the greater than sign here, or not equal to sign. And by the way, in this case, we can also use the not equal sign. That would be totally appropriate to use in any problems. It's just that in this case, we're testing the less than sign because we're assuming that based on the evidence that we're seeing that the sample mean is less than the population mean. So the next step then is to calculate the test statistic. And the test statistic, the formula is essentially given here. It's just z equals the sample mean minus the population mean divided by the population standard deviation over square root of n. If you remember, we had used this term last time. We had called this the standard error, right? And so we're just essentially saying that the test statistic z in this case, z for normal distribution because the population standard deviation is given, equals 7.6 minus 7.8 divided by the population standard deviation over square root of n. That's our test statistic. So the test statistic z equals minus 1.110. Now our task is to figure out what is the p-value, what is the probability that we obtain a z-score of minus 1.110. And what that means is that we're really testing is a sample mean of 7.6 unusual to get if the population mean is 7.8 and the population standard deviation is 0.57. That's really what we're testing. So we will go from the z, the test statistic z, to a p-value, and we will then compare that p-value to our threshold, which is the alpha of 0.05. So Professor Wan, I see that we have z equals minus 1.110, and we can calculate its p-value, which is given here. So how do we get this p-value?
You can use the z calculator, and that will give it to you automatically.
Correct. So and students can also use Python methods that they learned last week to do this calculation. So essentially what we're doing here is in this step, when we calculated the test statistic, we obtained the test statistic as z, and z is a standard normal. It's a z-score, so it's based on the standard normal distribution that has a mean of 0 and standard deviation of 1. We have standardized the data here. And so if we were to plot this, it would look something like this. The center value here is 0. So clearly minus 1.110 is on the left side of it. And then we are interested, based on the alternative hypothesis that the mean population mean is less than 7.8, the less than means the tail, the highlighted region, should be on the left side of the distribution. And what we need is the probability of that region. So recall that we studied this last week. We know how to calculate this. It comes out to be 0.133. That is the area under the curve for less than minus 1.110, which is our test statistic. So what we do is we compare the 0.133 to alpha of 0.05. If the rule is very simple, if the p-value is less than alpha, then we reject the null hypothesis. If the p-value is greater than alpha, then we do not reject the null hypothesis, and we say that the null hypothesis still holds. In this case, you can see that the p-value is much greater than the alpha. 0.133 is greater than 0.05. So we cannot reject the null hypothesis. So our conclusion at the end is that based on this hypothesis test, our p-value was 0.133, which is greater than alpha. Hence, we do not reject the null hypothesis, and we conclude that the manufacturer's claim that the smartphone has a mean battery life of 7.8 hours is okay. So in Python, we can use the z-test method from the submodule stats models.stats.weight stats. The z-test is the test in which case the population standard deviation is known. We've come up with data that has the standard deviation of 0.57. And essentially what we do is we're going to print the output of z-test method. The input to the function is the data itself. So here we have a sample data of 10 smartphones and their mean battery lives. And this data has the sample mean as 7.6. So we input that data here. Essentially we say x1 equals the Python pandas data frame of this list. So we convert it to a data frame and then we enter it into the function. And then the second input to the function is the value, which we set to 7.8. This is the value under the null hypothesis. Okay, so the null hypothesis, if you recall, was the claim made by the manufacturer that the mean battery life for their smartphone is 7.8. So that's the null hypothesis being input to the function. And when we run this, we get these two numbers. Now, please don't confuse this with the confidence interval. This is not the confidence interval. This is an output of the z-test method, which is a hypothesis test. So the outputs are the test statistic and its p-value. Okay, so we get our test statistic to be minus 1.113, almost equal to what we have in Zybooks. The little bit of variation is due to the data that we've chosen. And the associated p-value 0.265. So if we scroll to this case here, you'll see that the answer here is actually 0.133, and that's because in Python, this method z-test, it always returns two-tailed p-value. Okay, so it always returns the case when the alternative hypothesis is not equal. So because in our case we had chosen in the example that the alternative hypothesis is less than, meaning it's one-sided or one-tailed test, so what we will have to do is take this value and divide it by 2. So let's do that. So if I take this value, I'm going to just copy paste it here. I'll divide it by 2. And let's see what that comes out to be. So as you can see, I get 0.1328, which is approximately equal to 0.133. So the only bit of step involved here, other than get output of the hypothesis test, is that you have to know what alternative hypothesis you used. If we had used a two-tailed hypothesis test here, meaning if our alternative hypothesis was that the population mean is not equal to 7.8, then our answer here would have been two tails, one here and one here. Because it's symmetric, each tail would be the same value of 0.133. So the total would have been 0.266. Okay, but because we chose one-sided alternative hypothesis, so we have to divide the output that we get from Python here by 2. And when we do that, we get 0.133. So always remember, when you have an alternative hypothesis in which you're using the not equal sign, then you just take the output of Python, the p-value output of Python method, just as is. However, if you're using the alternative hypothesis, in which case you have the less than or the greater than sign, then you always have to divide this p-value or any p-value that you get by 2. And then that is the p-value for your hypothesis test. Now, in the real world, it's much more practical to use the student's t-test as opposed to the z-test, because often we don't know the population standard deviation, so we have to rely on the sample to use the sample standard deviation. And when we do that, the hypothesis test that we use is what we call the t-test. And in the t-test, you'll notice that the null and the alternative hypothesis are set up the same way as before. So there's nothing different about setting the null and the alternative hypothesis based on the problem statement that is given to you. What is different, however, is the test statistic and the way we calculate the p-value.
Now, if you look at the formula for the t-statistics, you're going to see that we will subtract the sample mean from the population mean, divided in this case not by the population standard deviation, which is unknown, but we're dividing by S, the sample standard deviation, over the square root of n. And in the case of the t-test, we need to use the degrees of freedom, which are always defined as n, the sample size, minus 1.
That is correct. Now, a quick clarification here. To get the t-test statistic, in this case is the t-statistic, it's equal to the sample mean minus the population mean, and then you divide that by the sample standard deviation over the square root of n. N is the sample size, and therefore, again, because we're using the student's t distribution, we always have to calculate the degrees of freedom. That equals n minus 1. And the rest of the steps are the same. Once you get to your test statistic t, you can get to the p-value by looking at student's t distribution, just like we were using the normal distribution. In Python, we have a method in scipy.stats to do this test for us. So let's use this example here, 5.5.2, to carry out this test, and we'll show you how this method works. So we're going to use the data that is stored in examscores.csv file. So we import it into a pandas data frame called scores, and we are going to work with the scores for exam 1. So there are 4 columns in this data set. Exam 1, 2, 3, and 4. We're only going to be looking at exam 1, and here is that sample data. So there are a total of 50 observations, and this column here represents the scores for each of those 50 students in exam 1. And we're testing the null hypothesis that the mean exam 1 score of any student, of anyone who has taken the class or will take in future, that the population mean of exam 1 is 82. And let's say, for the sake of solving this problem right now, we'll say that the alternative hypothesis that we're choosing is that the population mean is not equal to 82. Okay, so this is the data. So I'm going to comment this out, and now I will run the hypothesis test. As I said, this time we're going to assume that the population standard deviation is not given to us. That's a much more practical assumption in a lot of cases, that we are not given the population standard deviation, so we have to rely on the sample standard deviation and use that instead. So in scipy.stats submodule, we have a method that is called t-test1samp. So let's use the t-test1samp to carry out t-test, which is testing the hypothesis, but this time we're using the t distribution as opposed to the normal distribution. The inputs are very much the same as before. The first input is the data itself, and I'm using a pandas data frame, so that's what I'm entering here. And the second input is the value under the null hypothesis. So this time I'm using 82 because my null hypothesis is that the mean exam 1 score is 82. And I'll print this output. And so once I get this output, I get what we have here is the test statistic, the t test statistic. It equals 0.53, and we get our p-value, which is 0.5966. As you can see, the outputs are very much the same as before for a hypothesis test. You always get the test statistic and the p-value. Now, remember we had started off with an alternative hypothesis of not equal. We said that the alternative hypothesis is that the mean population exam score is not equal to 82. So when we get our p-value, remember that this is the two-sided p-value, so that is the p-value for this hypothesis test. If we had instead used an alternative hypothesis, let's say that we had used that the mean exam score is less than 82, then in that case, I would take this p-value and divide it by 2. Similarly, if we had chosen that the mean exam score is greater than 82, again, it's a one-sided test. So then again, I would divide this p-value by 2. So the only time I don't divide it by 2 again is when I choose not equal in my alternative hypothesis. So now that we have worked with hypothesis testing for the population mean, we now go over to hypothesis testing for population proportion. And the concept is very much the same. We have our null and alternative hypothesis. We get our test statistic. Based on the test statistic, we calculate our p-value. And then once we have the p-value, we make our conclusion by comparing it to the alpha. So Professor Wan, I see that the formula for test statistic looks different. So maybe we can go over this a little bit and discuss what it is.
Sure. So the formula for the Z statistic is similar to what we had before. The p hat, or the value that we're testing, in this case is 0.55 minus the p associated with the null hypothesis, or the sample, which is 0.47. Now we're dividing. In this case, the formula changes because we are dividing the p sub 0 value of 0.47 times the difference between 1 and 0.47 divided by the sample size, which in this case is 240.
That is correct. And just as Professor Wan said, since we're dealing with proportions, so clearly the test statistic is different in this case. The formula for it is different. It's just the p hat, which is the sample proportion, minus p naught, which is the proportion under the null hypothesis, and then divided by this piece here, p naught times 1 minus p naught divided by n. We plug in all these values, we get our test statistic. And once we have our test statistic and we see the direction under the alternative hypothesis, we can then calculate our p-value. So in this case, you can see that we have a right tail test, and therefore we have this normal curve. We look at the test statistic 2.483 and the area to the right of it. Okay, and then we get our p-value. So let's solve this example 5.6.1 in Python. A teacher found that 31 out of 50 students scored over 80 in exam 1. Now that is over the expected proportion of 0.5. So what that means is that the teacher expected approximately 50% of the class to score over 80 in the exam, but then found that 31 out of 50 actually scored over the 80. So in this case, the population proportion is 0.5. The sample proportion is going to be 31 divided by 50. So the alpha that we're given is 1% or 0.01. And the question is that, do we have sufficient evidence that the proportion of scores over 80 is greater than 50%. Well, we see it is greater. It's 50% of 50 students would be 25 students. So 31 students scoring over 80 is clearly a greater proportion than 50%. But is it statistically significant? That's what we're trying to test here. So here we have the proportions z-test method, which is in the submodule stats models, stats proportions. We can use this to carry out the hypothesis test for proportions. The inputs to it, the first input is the count, which is, in this case, in this example, it would be how many students actually scored over 80 in exam 1. So we saw that 31 students scored over 80. So that is the first input to the function. The second input is the number of observations equals 50. And then that is the input to the function. So the total number of observations are 50, so 50 students. And what the function does is it automatically calculates the proportion because you've given it the counts and the total number of observations. So it knows what the sample proportion is. The last input to the method is the value under the null hypothesis. And recall that in this case, because we're dealing with proportions, the null hypothesis value is a proportion of 50%. Okay, so the population proportion equals 50%, so we enter 0.50. And then once I have my method set up with all the inputs, I'm going to run this. And again, I will get the output here with two numbers. The first number represents the test statistic. The second number represents the p-value. And this is the associated p-value. And recall again, this is the p-value for a two-sided alternative hypothesis. So this assumes that my alternative hypothesis was not equal. Okay, so if my alternative hypothesis is not equal to 50%, then the p-value is 0.08. If, however, I chose my alternative hypothesis that the proportion is less than 50% or that it is greater than 50%, in both the cases, I would take this p-value and divide it by 2. So let's say in this case, my alternative hypothesis proportion being greater than 50% because we have 31 students out of 50 scoring above 80. And so if our alternative hypothesis is that the proportion is greater than 50% and we get our p-value as 0.04, then clearly we reject the null hypothesis that 50% of the class would be expected to score over 80. That is not the case based on the evidence we're seeing. So we conclude that in our case, in this case, more than 50% of the class will score over 80. Let's now move on to Module 3 discussion and the part that covers hypothesis testing. We're still using the same sample of size 50 that was generated for you. And recall that this sample is unique to all students, so all your answers will also be unique. The question now is that it has been claimed from the previous studies that the average diameter of ball bearings from the manufacturing process is 2.30. Now, based on the sample of 50 that you have collected, this is the sample that is being selected for you here in the Python script, is there evidence to suggest that the average diameter is greater than 2.3? And so the task is to perform a hypothesis test for the population mean at alpha 0.01. Based on this statement here, we know the different steps of a hypothesis test. They're actually given right here. Each of these questions that are included here are actually the steps that should be taken to perform a hypothesis test. So just based on this problem statement, Professor Wan, what would be the answer to the first question, where the question is define the null and the alternative hypothesis for this test in mathematical terms and in words?
Okay, so for the first step, we're saying that the null hypothesis will be equal with the equal sign that the null always carries to 2.3 centimeters, and the alternative hypothesis is greater than, which is equivalent to the area to the right of the z value.
That is absolutely correct. Just as Professor Wan said, the null hypothesis will be that the population mean diameter of ball bearings is equal to 2.30 centimeters, and the alternative will be that the population mean of the diameter of ball bearings will be greater than 2.30 centimeters. And remember to include the mathematical form and also a sentence explaining these two hypotheses. Okay, Professor Wan, what would be the answer to the second question? Report the level of significance.
In this case, this is included in the problem and is given as alpha to equal to 0.001.
That is correct. Recall that this alpha is used at the very last step when we compare the p-value with alpha. So the level of significance is 1%. We have to be sure that when we use the p-value that we use this properly. The proper way to use the rule is to say that if the p-value is greater than alpha, then we will not reject the null hypothesis. If the p-value is less than or equal to alpha, then we will reject the null hypothesis. So the third question is include the test statistic and the p-value and see step 3 in the Python script. Again, there's a reminder, note that Python methods return two-tail p-values, so you must report the correct p-value based on the alternative hypothesis. So Professor Wan, since we know our alternative hypothesis was that the population mean is greater than 2.30 centimeters, would we divide the output of Python, the p-value, would we divide it by 2 or would we not divide it by 2?
Well, as you said, Python returns the two-tail p-value. So in this particular case, we're looking at for the area greater than only. So we will have to divide the return p-value by 2 and then make the comparison with alpha.
Absolutely correct. Okay, so let's actually perform this step. Let's go to the Python script for module 3 discussion that involves hypothesis test and carry out this test. So here is the step for performing the hypothesis test. Since we are given the population standard deviation in step 1 and we have a sufficiently large sample size, so we will use the z-test to carry out this test. And if you recall, the z-test comes from the submodule that's given right here. The inputs to the z-test method is the data in a pandas data frame and the value under the null hypothesis. So we know from the question that the value under the null hypothesis is 2.30. So that's what we input here. The outputs to the method are the test statistic and the p-value. So we will get our test statistic and then we'll get our p-value and we will compare this p-value with alpha. So let's carry out this step. So here's the z-test hypothesis test for population mean. The test statistic comes out to be 2.90 and the two-tail p-value is 0.0038. So this is the two-tail p-value, 0.0038. So if we go back, recall that we had decided that since this is a one-sided test, one-tailed test, because the alternative hypothesis is that the average diameter is greater than 2.30, so we have to divide this p-value by 2. And when we divide this p-value by 2, you'll notice that the p-value will be less than alpha. okay, because alpha is 0.01. This two-sided p-value is already less than 0.01, so when we divide it by 2, the p-value for this test will be less than 0.01. So Professor Wan, since our p-value is less than 0.01, how do we answer this question? Provide your conclusion and interpretation of the test. Should the null hypothesis be rejected? Why or why not?
The answer is yes, it should be rejected since the p-value is less than 0.01.
That's absolutely correct. We will reject the null hypothesis, and then we will conclude that based on the evidence that we're seeing from the sample, we conclude that at 1% level of significance, the population mean diameter is not 2.30. It is greater than 2.30. Okay, and then in the follow-up questions, there are 2 follow-up questions. How do other students' confidence intervals compares with yours? So you just have to sort of comment on their confidence intervals. The second question is, if the population standard deviation is unknown and the sample size is not sufficiently large, would you still use the normal distribution to calculate these confidence intervals, or would you choose another distribution? If the latter, which distribution would you choose? So I think this is a good question for all students. Professor Wan and I have covered this several times in this lecture, so we will leave this to students to answer.